we'll talk about what is an adiabatic process, how to calculate work done in that kind of a process, change in internal energy and such things. So you all think about this and tell me, is it possible to raise the temperature of an object without supplying heat to it? Give me an example also if you think it is possible. Okay, I got one answer saying yes, by keeping another body which is hotter than this one in contact with it. See, if you keep another hotter object in contact, then it will provide heat. Heat transfer will take place through conduction, convection, or radiation, and due to that, the temperature will rise. But that is not what we are looking for. Okay, and I got another answer as no also. But no, I'll give you another minute. Think about it, both of you. Okay. Uh, The answer is yes, it is possible to raise the temperature without actually supplying heat to an object. Think about it this way. What happens when you rub your palms against each other for some time? Do they become warm or not? They do. Okay. Not just palms. Okay. You just rub any two objects against each other for some time, they do become warm. The temperature will rise. So when you rub your palms against each other, you didn't actually supply heat to them. And it's not like heat is getting transferred from one palm to the other also. Both your palms are at the same temperature and both their temperatures are rising. Okay. So can you think of an explanation to this? How is this happening? Or see, when you rub your palms against each other, temperature is definitely rising. If temperature is rising, obviously it's not an ideal gas. Your palm is not an ideal gas. It's made up of maybe solid, liquid, semi-solid, whatever it is. Molecules are present. Their temperatures are rising. Molecule temperature is rising means it's somehow getting energy. Okay. What energy or what is getting converted into the internal energy of molecules? When you rub your palms against each other, the internal energy of the molecules in your palms is increasing. Okay. What is getting converted into that internal energy? Think and give me an answer. I want answers from both of you. Right. I got one answer as kinetic energy is getting converted to internal energy of the molecules. Fine. Fine. Another answer as collision of molecules. Okay. You may say collision or you may say due to friction when palms are rubbed against each other. Due to friction, the temperature is rising. And but yeah, I asked about what type of energy is getting converted. Basically, when you are rubbing your palms against each other, no, there is friction between them and friction acts parallel to the surface, and there is displacement of the palm also parallel to the surface of contact. There is force, there is displacement, there is work being done. Okay, so basically what is happening here is work is getting converted to internal energy due to the negative work done by friction. Okay, wait, negative work only, no? Yeah, force is in one direction, relative displacement, yeah, due to the work done by friction, uh, you can say temperature is increasing. Fine. So what is getting converted to internal energy of the molecules? The energy in other parts of our body is getting converted to internal energy of these molecules on your hands, on your palms. Fine. Obviously, your body's energy is getting used up in this process, no, of rubbing your palms. So that is getting converted to the internal energy. Now, that or something like that is what happens in an adiabatic process. In an adiabatic process, no heat is supplied or removed from the system. Okay, so delta Q tends to zero. Usually, the system we consider in thermodynamics is an ideal gas. So we don't supply heat to it, we don't remove heat from it. That is what happens in an adiabatic process. So, what happens in a adiabatic process at all? Internal energy gets converted to work, or work gets converted to internal energy. Okay, we know from the first law of thermodynamics that delta Q, the heat supplied to a system, is equal to the change in its internal energy plus the work done by the gas. Okay. Now, if this term is zero, then automatically the other two terms will be negatives of each other. That means change in internal energy will be negative of work done by the gas. So if the gas is actually doing some work, okay, if this term is positive, change in internal energy will be negative. What does change in a quantity being negative mean? That quantity is decreasing. So if work is being done, the gas loses internal energy. Internal energy gets converted to work. Okay. Suppose work is being done on the gas. Okay, means delta W is negative. Work done by the gas is negative. Then change in internal energy will be positive. If work is done on the gas, work done by the gas will be negative. And if work is done on the gas, means we are supplying energy to the gas in the form of work that gets stored as internal energy. Okay. So in an adiabatic process, work to internal energy or internal energy to work conversion is what happens. Okay. Let's discuss some, what do you say, details about this process. So delta Q is 0, 0 or tending to 0, almost equal to 0 also, you can say, nothing wrong in that. And delta U is negative of delta W. So without supplying heat, you can expect temperature changes to occur in an adiabatic process. Fine. Now let's consider this case itself. First case, just a moment. First case, suppose delta U is positive and delta W is negative in adiabatic process. One of you quickly tell me, what is the general formula for delta U, change in internal energy? What is the formula we have been using? Okay, I got one answer as F by 2 NR delta T. That is correct. Delta U is F by 2, where F is the number of degrees of freedom, NR delta T. Now, delta U is positive. That means change in temperature is positive. That means temperature is increasing. Okay. If that happens in an adiabatic process, if internal energy increases, then the work done by the gas will be negative. Now, what is the formula, general formula for work done? Integral P dV. Pressure of a gas can never be negative. But here work done is negative. That means dV is negative. Change in volume is negative. Therefore, if temperature increases, volume decreases in an adiabatic process. Okay. Temperature is increasing, volume is decreasing. Now, I want you all to consider the fact that it's an ideal gas. Ideal gas has to follow the equation of state PV is equal to nRT. If temperature increases, volume decreases. Based on that, you all tell me what happens to pressure. If temperature increases and volume decreases, what happens to pressure? Think carefully and answer, all of you. Okay. Uh, you were asked to comment on what happens to pressure. I got one answer as increases, another also as increases. That is correct. Okay. Now PV is equal to nRT. So you can say P is nRT divided by V. Okay. We are not going to change the number of moles. The amount of gas will remain fixed. Now I told you that temperature is increasing and volume is decreasing. See, temperature is in the numerator. If it increases, the fraction increases. Volume is in the denominator. If it decreases, then also the fraction will increase. Okay. So the pressure will increase. Right. So in an adiabatic process, if temperature is increasing, pressure will also increase, volume will decrease. Okay. Now it's also possible that in an adiabatic process, the change in internal energy is negative and work done is positive. Means internal energy decreases and gets converted to work. Okay, that possibility is also there. If that happens, change in internal energy negative means what? Temperature decreases. Work done is positive means what? Volume increases. Okay. If temperature decreases, volume increases, pressure will decrease. So remember that in an adiabatic process, Temperature and pressure follow one pattern, volume does the opposite. Okay, it's always like that in an adiabatic process. And also note that all three thermodynamic state variables, temperature, volume, and pressure, will undergo a change in an adiabatic process. None of them remains constant. Okay. Now, for all thermodynamic processes that we have discussed so far, isothermal, isobaric, and isochoric, what we did was we drew the indicator diagrams, process diagrams, and then we discussed delta Q, delta U, delta W. Okay. We have to do the same for adiabatic process also. You should know how to calculate work done, uh, change in internal energy and such things, and you should be able to draw the graph also. Now, how did we draw the graphs for other processes? We drew graphs based on this equation, PV is equal to nRT. For isothermal, isochoric, and isobaric, one of the state variables used to be constant. Then we could easily write the equation for the other two and draw the graphs. Okay, mostly we used to get straight line equations or pressure inversely proportional to volume. That graph was a rectangular hyperbola. But now all three are changing. Okay, then it becomes difficult to draw the graph directly based on this equation. We need more information. Why? Suppose you want to draw the PV graph, then you need to know how pressure varies only with volume. Temperature should not be there, or another variable should not be there. Okay, but in an adiabatic process, all three are variable. That is what makes this process slightly tricky to deal with. Okay, slightly difficult to deal with. So suppose you want the PV graph, you need an equation only between pressure and volume. So you need to eliminate temperature from the ideal gas equation. How can that be done? We need some more information, as I said. And the only information we have about an adiabatic process is that delta Q is zero. Heat is not supplied or removed from the gas. So let's try to make use of that. And follow this derivation carefully, all of you. This is very important. Now, delta Q we know is delta U plus delta W, basic first law of thermodynamics. This can also be written as dq is equal to du plus dw. Now, in an adiabatic process, dq is 0. So, du becomes negative of dw. Fine. By definition, internal energy, okay, we had discussed this in, I think, the first lecture of thermodynamics itself. By definition, internal energy is given by F by 2 nRT, okay, from Maxwell's law of equipartition of energy. Then du becomes F by 2 nR dt. Small change in internal energy can be expressed as F by 2 nR, small change in temperature, is equal to negative of dw is nothing but pdv. Okay. Generally in mechanics, we write dw is equal to F dot ds. When it comes to work done by a gas, this same expression changes to pressure multiplied with the small change in volume. Okay, dw is pdv. So why are we doing this? If you observe here, we are relating temperature, pressure, and volume through another equation, first law of thermodynamics. Okay, now they are already related through PV is equal to nRT, but if you can relate them through another equation also, then by dividing those two equations or substituting one term from that equation in this equation, you can eliminate one of the variables. Okay. See, there are three variables, pressure, volume, and temperature. We have two equations. So we won't be able to solve for all three of them, but we can eliminate one of them. That is the idea. So we'll keep this equation aside. Next, we have PV is equal to nRT. Differentiate this equation. Now we know all three are variables, pressure, volume, and temperature. If you differentiate PV is equal to nRT, what does the left-hand side become? Two variables are multiplied, so you'll have to use the product rule. P multiplied with dV by, you can differentiate with respect to any random variable, let it be P dV by dx plus V dP by dx is equal to nR dt by dx. The dx's will get cancelled anyway, so it doesn't matter with respect to what you differentiate. Okay, so what do you end up getting? You get P dV plus VdP is equal to nR dt. Okay. Now the most common graph that we draw for any process is the PV graph. To draw the PV graph, you need an equation between pressure and volume. So temperature should be eliminated. How are we going to do that? We will take nR dt from this equation. Okay. From this equation, what does nR dt become? Minus P dV divided by F by 2, where F stands for degrees of freedom. So it depends on the type of gas. We will substitute this value of nR dt over here. That's all. Then only pressure and volume will be there in the equation. Okay. So you can write this as equal to minus P dV divided by F by 2 becomes minus 2 by F P dV. Okay. Now send P dV that side. You get P dV plus 2 by F P dV, that is 1 plus 2 by F times P dV plus VdP is equal to 0. Okay, just a rearrangement of the equation. Fine. So we can say that 1 plus 2 by F P dV will be negative of VdP. Now we keep the pressure terms on one side, volume terms on the other side. You can say 1 plus 2 by F dV by V. Okay, send the volume to denominator on this side, and then we'll send pressure to the denominator on the other side, is equal to minus dP by P. Okay. Now look at this term, 1 plus 2 by F. 1 plus 2 by F can be written as F plus 2 divided by F. Now, when we talked about isobaric and isochoric processes, we derived their molar specific heats. For an isobaric process, we got molar specific heat as F plus 2 divided by F multiplied with, okay, wait, F plus F by 2 plus 1, that is F plus 2 divided by 2. Or, okay, let me write it the way we derived only. We derived it as F by 2 plus 1 multiplied with R. That is Cp for any gas. It depends on the number of degrees of freedom. And Cv for any gas was F by 2 multiplied with R. Okay. Divide these two equations. Divide Cp and Cv of a gas. So the left hand side becomes Cp by Cv. Right hand side becomes R gets cancelled and you will be left with F plus 2 divided by F. And that is what we see here. Cp by Cv. Okay. Cp is molar specific heat at constant pressure. Cv is molar specific heat at constant volume. Their ratio is F plus 2 divided by F. We call this as gamma, or we denote this by gamma. It's called the adiabatic quotient. Okay, or adiabatic ratio, Cp by Cv, or ratio of molar specific heats also you can call it. So this 1 plus 2 whole, okay, 1 plus 2 by F, which is F plus 2 divided by F, can effectively be written as gamma, which is nothing but Cp by Cv. So the equation becomes slightly simpler now. Gamma times dV by V is equal to minus dP by P. So what do we finally arrive at? We arrive at an equation which only has pressure and volume in it. Okay, but there are differential or small changes, dP, dV. We still cannot draw a graph directly based on this equation. We need only P and V terms. We should not have dP, dV terms. Okay. So integrate both sides. Gamma is a constant anyway. For a given gas, Cp, Cv, they depend on the number of degrees of freedom. So Cp and Cv depend on the type of gas. Gamma also depends on the type of gas. So integrate both sides. What is integral dV by V? It becomes ln V. Okay, because generally integral 1 by x dx is ln x. Okay, so left hand side becomes gamma times ln V. We still have to substitute limits. We'll do that. Is equal to right hand side becomes minus ln P. Okay. Gamma ln V, some basic properties of logarithm. Ln of x to the power of a is a times ln of x. Okay, I hope you all know this. So gamma times ln of v can be written as ln of v to the power of gamma. Okay, and the right hand side I'll bring to the left hand side, becomes plus ln of p is equal to 0. Okay, what does that mean? Log a plus log b is log of a multiplied with b. So you can say ln of pv power gamma. We still have to substitute limits. Okay, we didn't do that. So ln of pv power gamma from initial pressure, initial volume to final pressure, final volume is equal to 0. Okay, wait, how did we get a 0 here? We integrated both sides and okay, yeah, that's fine. So what does this show us? This shows us that ln of p final v final power gamma minus ln of p initial v initial power gamma is 0. This means P final V final power gamma is equal to P initial V initial power gamma. These two terms must be the same. Okay. What does that mean? That means the product of PV power gamma must be the same always. Okay. So PV power gamma is equal to constant. This is how pressure and volume are related in an adiabatic process. Fine. Let's quickly go through the derivation once. Our aim here is to derive a relation only between pressure and volume so that we can draw a graph between them. And if you know the relation between pressure and volume, you can even try to calculate work done using that. Okay. The problem here with an adiabatic process is that all three state variables, pressure, volume, and temperature, are variable. So directly from the ideal gas equation, you cannot get a relation exclusively between pressure and volume. You'll have to eliminate temperature. Okay. For that, what we did is we made use of the first law of thermodynamics in its differential form. And we wrote ideal gas equation also in its differential form. PdV plus VdP is equal to nRdt, as you can see on the screen. And nRdt from the first equation was substituted in the second equation. Temperature got eliminated. But we had these terms dP and dV. So we kept all pressure terms on one side, volume terms on one side, integrated both sides such that dP, dV don't appear in the equation anymore. And finally, we see that PV power gamma becomes constant. Okay. Now we will be able to draw a graph. But see, in this process, we introduced a new term called gamma, which is basically Cp by Cv. Note this down, all of you, in case you don't know it. Okay. Cp is F by 2 plus 1 multiplied with R. Cv is F by 2 multiplied with R. If you divide them, this is what you get, F plus 2 divided by F. Okay. So based on this formula, gamma is equal to F plus 2 divided by F. I want you all to tell me what is gamma of a monoatomic gas, what is gamma of a diatomic gas, and what is gamma of a polyatomic gas. I hope you remember the degrees of freedom. Based on that, write these values, all of you. Okay, I haven't received any answers yet. How many degrees of freedom does a monoatomic gas have?
Three, sir.
3. Okay. And all three are translational degrees of freedom. If degrees of freedom is 3, then gamma becomes 3 plus 2 divided by 3. That is 5 by 3. That's all. 1.66 or 1.67, we can say. Next, how many degrees of freedom does a diatomic gas have or a molecule have? We assume molecules to be rigid. Okay. So no vibrational degrees of freedom will be considered. In that case, there will be 5 degrees of freedom for a diatomic gas. 3 translational, 2 rotational. It can store rotational kinetic energy as well. So if there are 5 degrees of freedom, then 5 plus 2, 7 divided by 5 will become the gamma of a diatomic gas. 7 by 5 is 1.4. Next, polyatomic gas. Polyatomic non-linear, we assume they'll have 6 degrees of freedom, 3 translational, 3 rotational. Okay, again, vibrational are ignored. We assume molecules to be rigid. So 6 degrees of freedom, then 6 plus 2, 8 divided by 6. 8 by 6 is 4 by 3. 4 by 3 is close to 1.33. Okay, so these are the gamma values for different types of gases. You can even have a mixture of gases. For that, how to find out gamma, we'll discuss a little later. So remember, monatomic has the highest gamma value, followed by diatomic, and the least is for polyatomic. Okay. Now, we need to draw the PV graph based on this equation. PV power gamma is equal to constant. You can observe that whatever be the type of gas, even if it's a mixture, gamma will always be greater than 1. Okay. Cp by Cv has to be greater than 1. Okay. Why should it be like that? One way you can justify mathematically is Cp minus Cv is equal to R. You must be knowing that. We had discussed this in the last class also. So if Cp minus Cv is a positive value R, that means Cp is a bigger term than Cv. Okay. So Cp by Cv, that ratio has to be greater than 1. Another way to justify is that, uh, uh, see, C is nothing but molar specific heat, right? Molar specific heat, by definition, is the heat required to raise the temperature of 1 mole of a gas by 1 unit. Okay, that is what is molar specific heat by definition. So suppose there is 1 mole of a gas and you want to raise its temperature by 1 unit. What heat you need to supply, you have to think. Now Cp stands for molar specific heat at constant pressure. Cv stands for molar specific heat at constant volume. Now when you supply heat to a gas, basically what happens, some of it gets stored as internal energy, some of it gets converted to work. If you keep volume constant, okay, let's talk about Cv. If you keep volume constant, you are not allowing the gas to expand. If you are not allowing the gas to expand, you are not allowing it to do work. Then all the heat supplied gets stored as internal energy only, no? That will lead to a greater rise in temperature. If you allow it to expand, some of the heat gets converted to work, only some part gets stored as internal energy. But if you don't allow it to expand, all the heat gets stored as internal energy. That will lead to a greater rise in temperature or an easier rise in temperature. That is why at constant volume, you will need lesser heat to raise temperature by 1 unit. Whereas at constant pressure, expansion must be allowed. So work will be done by the gas. So you will need more heat to raise its temperature. Okay. That is why Cp is greater than Cv. That is the, uh, what can you say, more meaningful explanation rather than writing the mathematical expression. Okay. At constant volume, gas is not allowed to do work. So all the heat supplied results in a temperature rise. So you will need only a little bit of heat to raise the temperature by 1 unit. On the other hand, at constant pressure, you should allow the gas to expand. So all the heat you supply won't get stored as internal energy. Some gets converted to work. So only a part of the heat results in a temperature rise. So you'll need to supply more heat for a 1 unit rise in temperature at constant pressure compared to constant volume. That's why Cp is more than Cv. Okay, not just for an ideal gas, generally for any object, any material, Cp will be more than Cv only. Okay. So gamma will be greater than 1. Now the equation we have here is PV power gamma is equal to constant. There are two terms being multiplied. Pressure is one term, V power gamma is the other term. If the product of two terms has to be constant, then when one increases, the other has to decrease. Okay. And we had discussed this at the beginning also of today's class, that temperature and pressure follow one pattern, volume follows the other pattern in an adiabatic process. So if pressure increases, volume has to decrease. And if pressure decreases, volume will have to increase. Okay. They are not inversely proportional. It's not like PV is equal to constant if and P becomes inversely proportional to V. It's not like this. Okay. If one increases, the other decreases, but they are not inversely proportional to each other. So if you draw a graph, pressure on y-axis, volume on x-axis, usually that is how we keep it. Okay. You know that when one increases, the other has to decrease. So the graph will look somewhat similar to that of an isothermal process, but it's not exactly the same, because for an isothermal process, the governing equation is PV is equal to constant. But here PV power gamma is equal to constant. Okay. So this is the shape of the graph, shape of the PV graph in an adiabatic process. Okay. So it's all based on this equation. Fine. Next, suppose you want to draw the volume versus temperature graph. This also we had discussed at the beginning of this class itself. Temperature, pressure follow one pattern, volume follows the other pattern. So here also, if temperature increases, volume has to decrease. And if temperature decreases, volume has to increase. So the graph will look somewhat similar to this. But let's discuss the equation as well. In an adiabatic process, we have proved that PV power gamma will be constant. Now this relates pressure and volume, but we need a relation between temperature and volume. How to do that? In place of P, you can write nRT divided by V from ideal gas equation multiplied with V power gamma is equal to constant. Okay. N and R are anyway constants. Merge them with the constant on the other side. What will you be left with? Temperature into V power gamma divided by V. V power gamma minus 1 is equal to constant. That is the governing equation for the TV or a VT graph. Gamma is greater than 1. If gamma is greater than 1, gamma minus 1 will still be a positive power. Okay, positive exponent. So if temperature increases, volume has to decrease for that product to remain constant. So the temperature volume graph, it will look similar to the pressure volume graph. It's not exactly the same equation, but their graphs will look somewhat similar. Okay. What varies is the steepness or the slope of the graph. Because for one equation, for one graph, the equation is PV power gamma is constant. For the other graph, the equation is TV power gamma minus 1 is constant. Okay, slightly different equation. So there will be a slightly different graph. Okay. Next, pressure temperature graph in an adiabatic process. Now we had discussed analytically or qualitatively that temperature and pressure follow the same pattern. If temperature increases, pressure also has to increase. And if temperature decreases, pressure has to decrease. Now, how to draw a graph between them? Let's see. We need the equation first. In an adiabatic process, we know PV power gamma is constant. Okay. We want to relate pressure temperature now. So you'll need to eliminate volume, and that can be done this way. Volume can be written as nRT divided by P is equal to constant. Now n and r are constants. We'll send them to the right hand side and merge it with the already existing constant. What you will be left with is P multiplied with T power gamma divided by P power gamma is equal to constant. Okay. So T power gamma, P divided by P power gamma becomes P power 1 minus gamma is equal to constant. That's the relation between temperature and pressure in an adiabatic process. Okay. Now you know gamma is more than 1. If gamma is more than 1, this power is positive. The power of temperature is positive, but the power of pressure becomes negative. Okay. One of the terms having a positive exponent and the other having a negative exponent. That means one of them is in the numerator, the other is in the denominator. Okay. And that has to remain constant. So when numerator increases, denominator will also have to increase. Or when numerator decreases, denominator will also have to decrease. That's why temperature, pressure either both increase or both decrease in an adiabatic process. Okay. Now you need to draw a graph between them. See, this is definitely not a straight line. The equation is not of a straight line. T power gamma, P power 1 minus gamma does not represent a straight line. Okay, it's like y power gamma, x power 1 minus gamma is equal to constant. Straight line equation must have been of the form y is equal to mx plus c. It's not like that. Okay. Then suppose you take pressure on the y-axis, temperature on the x-axis. You know both of them should increase and both of them should decrease. And that increase or decrease should happen non-linearly. Then two possibilities will arise. Pressure, temperature both increasing non-linearly could happen like this, with the graph being concave downwards. Okay. Or pressure, temperature both increasing simultaneously and non-linearly could also happen like this, with the graph being concave upwards. Okay. This is A, this is B. You need to decide, okay, which is the correct representation. Can any of you tell me which graph will be appropriate? Should it be concave downwards or should it be concave upwards? Little bit of mathematics will be involved here. The pressure temperature graph of an adiabatic process. Okay, let me explain the difference between these two graphs. Suppose you have a graph which is concave downwards. Okay, the graph A that I have drawn. This is Y, this is X. Some random quantities you take, and let's say the graph between Y and X is like this. Okay, understand what this graph is trying to tell you. Since it is becoming more horizontal, okay, as X increases or as you go higher and higher, it tends to become parallel to the X axis. What does that mean? That means even for a small change in Y, okay, this is a small change in Y, there will be a large change in X as you go to higher and higher values. That is what it means. Suppose you have the other graph, okay, or suppose you have, or you draw the graph the other way. Let's say the graph is concave upwards, like this. What does this graph say? This says that as you go to higher and higher values, for a small change in X, there will be a large change in Y. Okay, that's the difference between these two graphs. Now we took pressure on the y-axis and temperature on the x-axis. So when you go to higher and higher values, which term changes more rapidly is what determines which graph is correct. Okay, whether pressure will increase more rapidly or temperature will increase more rapidly is what determines the nature of the graph. If you consider graph A tends to become parallel to the x-axis, means there will be a large change in the x coordinate for a small change in y coordinate. So if temperature changes are going to dominate, then it will be graph A. If pressure changes are going to be much higher than temperature changes, then it will be graph B. So you have to determine which one changes more rapidly. And that can be done by using this equation. So think about it. I'll give you all 2 minutes. Which graph do you think suits an adiabatic process? Okay, I got one answer as option A. So what that means is as you go to higher and higher values, temperature tends to increase more rapidly. Okay, there is a more rapid change in temperature compared to the change in pressure. Let's see. Look at the equation we have. T power gamma, P power 1 minus gamma is equal to constant. See, this is actually a very in-depth discussion. You won't find this in books, but it's important to understand why the graph is drawn in a particular manner. Okay. Now this can be written as T power gamma divided by P power gamma minus 1 is equal to constant. So the power of the numerator is greater than the power of the denominator. So you take it like this. Let's use some random numbers. Let's say x. Okay, we took temperature on which axis? X axis, no? Okay. Let's say x power 5 divided by y power 4 is equal to constant. So x power 5 should be proportional to y power 4. Now x is raised to the fifth power, y is only raised to the fourth power, but these two increase in the same manner. Then you tell me, should x increase more rapidly or y increase more rapidly?
Y should
Y should increase more rapidly, correct? Because it's only raised to the fourth power, but it should compete with the fifth power to which x is raised. Okay, so y will have to rise more rapidly compared to x. Now, what do we have on the y-axis? Pressure. Pressure will have to rise more rapidly. Then answer will be option B. Okay, that is how the pressure temperature graph of an adiabatic process looks. Okay. So these are the process diagrams or indicator diagrams for an adiabatic process. As I said, slightly tricky because all three are variable. We first derived the equation PV power gamma is constant. Based on that, we drew the PV graph. Then from PV power gamma is equal to constant itself, we derived a relation between temperature and volume. TV power gamma minus 1 is constant. We drew the graph. Then pressure temperature graph. And questions based on these equations are quite common. Okay. They can give you the gamma value and ask if volume is doubled, what happens to pressure? Okay, let's solve one simple question like that. Okay. In an adiabatic process itself, uh, let's say initial pressure is P naught, initial volume is V naught, and the gas is expanded to, let's say, 4 times its initial volume. They will give you the type of gas also. Let's say it is diatomic gas. The gas is expanded to 4 times its initial volume. Then how much is the final pressure? Okay, answer should be in terms of initial pressure, P naught. Do this, all of you. So you know what is done to the volume and you have to tell what happens to the pressure. So think of the relation between them. The relation between them is PV power gamma is equal to constant. So P1 V1 power gamma. What is gamma for diatomic? Gamma basic formula is F plus 2 divided by F. Diatomic has 5 degrees of freedom. So 5 plus 2 divided by 5, 7 by 5. So P1 V1 power 7 by 5 is equal to P2 V2 power 7 by 5. That's all. P1 V1 power gamma is equal to P2 V2 power gamma. Initial pressure is P naught, volume is V naught, 7 by 5 is equal to final pressure is what we need to find out. Final volume is 4 times the initial volume. Then that will be raised to the power 7 by 5. This can be written as P final 4 to the power 7 by 5, V naught to the power 7 by 5. And on left hand side, you have P naught V naught power 7 by 5. That V naught power 7 by 5 will get cancelled. That's all. From this, you get the final pressure. And you don't have to know what is 4 power 7 by 5. They will either give it to you in the question or the options will be in terms of that. Okay. So initial pressure divided by 4 power 7 by 5. That's the final pressure. Such questions will, such questions are quite common in an adiabatic process. Okay, so we have drawn the process diagrams, PV, VT, and PT graphs. Now, see, whatever we have derived today is very important. You need to do all this on your own. Okay, basically, what is an adiabatic process? A process in which we don't supply heat or remove heat from the gas, but still work will be done by the gas. How? Internal energy gets converted to work, or the reverse can happen. Okay, so if internal energy decreases, means internal energy is lost, that means some work is being done, or reverse. If internal energy increases, that means someone did work on the gas. So work done by the gas will be negative. So they'll have opposite signs. And based on that only, we have derived everything. We first discussed how temperature, pressure, and volume vary. Temperature, pressure follow one pattern. Volume follows the opposite pattern. If T and P increase, V decreases. If T and P decrease, V increases in an adiabatic process. Then we derive the relation between pressure volume by writing ideal gas in differential form and first law of thermodynamics in differential form. That derivation is very important. You should be able to do it. After that, we drew the graphs. Okay. Next, let us also discuss how to calculate delta Q, delta U, delta W in this kind of process, then molar specific heat, then bulk modulus, all that discussion. Let us finish it off. So, first thing, delta Q in an adiabatic process is obviously zero, but that is by the definition of the process itself. No heat is supplied or removed from the gas. Okay, delta Q is zero. Next, delta U. Delta U in any process can be calculated as F by 2 nR delta T. So, if you know the type of gas, number of moles, and the temperature change that is happening in the adiabatic process, you can use this directly to tell the change in internal energy. But sometimes, as I said, questions in thermodynamics will either be given in terms of temperature or in terms of pressure volume. Okay, so you should know how to do this in terms of pressure volume also. So you will need to replace delta T, or you will need to express temperature in terms of pressure and volume. And that can be done using ideal gas equation. We know PV is equal to nRT. Okay. So the change in the left hand side of this equation should be equal to change in the right hand side of this equation. Okay. Now N and R are constants. So the right hand side becomes nR delta T. Left hand side, neither of them is constant. Pressure, volume are both variable. Then how do you write change in PV? You can't write it as P delta V. You can do that if pressure is constant. You can't write it as V delta P also. You can do that if volume is constant. Here both are variable. So the only thing you can do is P final V final minus P initial V initial is equal to nR delta T. So in place of nR delta T, you can even substitute this. Okay. Therefore, the change in internal energy in an adiabatic process can also be calculated as F by 2 times P2 V2 minus P1 V1. Okay. And in many books, this is written in a slightly different manner. I prefer this actually. This is much easier. But they write it in terms of gamma. In terms of gamma, it gets complicated. Gamma is what? F plus 2 divided by F, right? So it can also be written as 1 plus 2 by F, which can also be written as gamma minus 1 is equal to 2 by F. If gamma minus 1 is 2 by F, 1 divided by gamma minus 1 will be F by 2. So in place of F by 2, they put this 1 by gamma minus 1 here. Then what does change in internal energy become? P2 V2 minus P1 V1 divided by gamma minus 1. It can be expressed like that also. Okay? But understand, F and gamma are not independent quantities. If you know F, you know gamma. If you know gamma, you know F. Okay, you can convert one to the other. So in terms of pressure and volume, if you want to find out the change in internal energy in an adiabatic process, you can use this. Okay. But anyway, don't memorize these formulas. You don't have to. Okay. Understand how to derive them whenever necessary. Quickly, within 2 seconds, you can do this. See, the basic formula is F by 2 nR delta T. If temperature changes are known to you, you can use this directly. In case pressure volume changes are given to you, you will have to replace nR delta T with P final V final minus P initial V initial. Okay, because I mean, why I'm asking you not to memorize the formula is because in the final exam, under that stress or tension, whatever it is, just a small mistake in the minus sign is enough to give you wrong answers. And the wrong answers will definitely be there in the options. Okay, suppose you forget whether it is P2 V2 minus P1 V1 or P1 V1 minus P2 V2, interchanging of terms. Any one small mistake, the answer will go wrong. Okay, so you don't have to memorize formulas for each process separately. Remember the fundamental formula. For delta U, the fundamental formula is F by 2 nR delta T. From there, how to make it specific for that process, you should know how to do. Then you are on the safer side. There's lesser chance of making mistakes if you are conceptually strong. Okay, so practice these derivations. So this is how you can find out the change in internal energy in an adiabatic process. So it all depends on what information is given in the problem. Next, work done in an adiabatic process. See, work done, the fundamental formula is integral P dV, but that way it will be difficult to proceed in an adiabatic process. Why? To do this, you need to know the equation relating pressure and volume, which we don't know. We only know PV power gamma is constant. We don't know what that constant is. Okay. And substituting that in place of pressure here, integrating and all is complicated. But what advantage we have in an adiabatic process, delta Q is 0. So delta U is simply negative of work done. No. So work done is just the negative of change in internal energy. Simple. Therefore, you can express work done in an adiabatic process or calculate work done in an adiabatic process as negative of F by 2 nr delta T. Simple. Or you can also write negative of F by 2 nr delta T is P2 V2 minus P1 V1. Or you can also write negative of P2 V2 minus P1 V1 divided by gamma minus 1. Okay. F plus 2, sorry, F by 2 is 1 by gamma minus 1. That's what I have used here. So in any one of these methods, you can calculate work done in an adiabatic process. Not difficult at all. You just need to know the fundamental formula. And what happens to first law of thermodynamics? Delta Q is delta U plus delta W. It changes to delta W is negative of delta U in an adiabatic process. Based on that, we are writing the expression for work done. So this is how delta Q, delta U, and delta W can be calculated in an adiabatic process. They will give you all the necessary information and you can find out. Okay. Next thing that we discuss for any process is molar specific heat. By definition, molar specific heat is delta Q divided by N delta T. In an adiabatic process, this is 0. Temperature change happens. Okay, denominator is non-zero. How does temperature change happen without supplying heat? Work gets converted to internal energy or internal energy gets converted to work. Okay, so temperature can increase, it can decrease depending on the process. So delta T will be non-zero, but delta Q is 0. Then that makes molar specific heat 0. So molar specific heat of an adiabatic process is 0. Next, bulk modulus in an adiabatic process. Can one of you quickly tell me the basic formula for bulk modulus? We had done this for isothermal, isobaric, isochoric. What formula do we use? Yusuf,
So volumetrics strain by stress.
it is stress by strain.
Yes.
Okay. Anyway, this is the definition of bulk modulus. Fine. So that changes to minus delta P divided by delta V by V. That is minus V delta P by delta V. But I can't do this every time. I mean, when it comes to ideal gas, we apply this in this form. Minus V dP by dV. Small changes. Okay, this is what we have been using to find out the bulk modulus for a given process. Okay, now to be able to calculate this or express this in a convenient manner, you need to know how pressure varies with volume. Now, in an adiabatic process, PV power gamma is equal to constant. Okay, from there, we should somehow get dP by dV. Okay, the only way we can get dP by dV from this is by differentiating this. Pressure is variable. V power gamma is also variable. Two variables are being multiplied. So you have to use the product rule to differentiate. So pressure multiplied with derivative of V power gamma becomes gamma times V power gamma minus 1 dV by dx. I'm assuming I'm differentiating with respect to some variable x. Plus V power gamma multiplied with derivative of pressure is simply dP by dx, should be derivative of constant on the right hand side is 0. Okay, now you can remove this dx. Doesn't matter with respect to what you differentiate. So what are you left with? Gamma p v power gamma minus 1 dv is equal to negative of v power gamma dp. Now, on one hand, you have v power gamma minus 1. On the other side, you have v power gamma. Cancel these. It simply becomes v. Okay. Therefore, you can write gamma p is equal to minus v dp by dv. And this itself is bulk modulus. Therefore, bulk modulus in an adiabatic process is gamma times the pressure. Obviously, this is not a constant because pressure keeps changing in an adiabatic process. So the bulk modulus also keeps changing. What does that mean? What does bulk modulus changing mean? Bulk modulus tells you how hard it is to compress the object. Okay, greater the bulk modulus, more difficult it is to compress it. So if bulk modulus varies with pressure, it means greater the pressure, more difficult it is to compress the gas in an adiabatic process also. Okay, again, this derivation is also important. Anyway, see, for most of you, the 11th class board exam is done. So this will be, I mean, for board exam, this is actually important, but in exams like JEE Advanced also, derivations are very useful. Okay, they can give you a random process. Okay, they can give you a process something like this. Say P power 5, V power 4 is equal to constant. Some process they have given, and they can ask you what is the bulk modulus in this process. You should know what to do, no? This doesn't look like an this doesn't look like an adiabatic process equation. Okay, some random process is given to you, or they can give you a slightly different type of equation also. So you have to know how to derive it from the fundamentals. Minus V dP by dV. So the pressure volume equation has to be differentiated, and you should obtain dP by dV from it and put it here. Then you can get the bulk modulus. Okay, all the derivations are important. That is why we are spending so much time doing them. Unnecessary derivations I will also not explain. Fine. So molar specific heat is done. Bulk modulus is also done. Okay. Problems based on adiabatic process we will do in tomorrow's class. So we have discussed all four basic thermodynamic processes: isothermal, isochoric, isobaric, and adiabatic. In each process, we know how to calculate anything that is asked: work done or heat supplied or change in internal energy. We know how to draw the graphs also. Okay. So tomorrow's class will be solving problems based on all these. So make sure you revise thoroughly. And today I will upload all these lectures. If you have missed any part also, you can go through it. Fine. Thank you all. We'll continue tomorrow.
Thank you, sir.